not that far ago, I was working at Google in Zurich, so it's really great to be back in Switzerland and talk about one of my favorite tools out there. So I'm definitely going to enjoy my talk. I hope you will too. And yeah, let's get going. Feel free to interrupt me if you have questions. There's plenty of time for questions at the end, but if there's something really stringent, just go for it. So for those of you who don't know what's TensorFlow, so what am I going to spend the next half an hour talking about? TensorFlow is an open source machine learning library, and it's primarily aimed at deep learning. So this deep learning is this new branch of machine learning that has been basically sweeping the world away with its ability to solve new problems. So a lot of problems that we thought are not solvable 5 years ago have already been solved using deep learning. And some of the really core feature of TensorFlow, and I really cannot stress this enough, is that it's made both for research and production. So the same framework works, and it's applicable very well for research work, but you can also really take that model that the researcher made and just deploy that. And it comes with a very flexible license, so you can just take it and use it in your product or your projects, however you like. So just as a brief introduction, I'm going to talk to you a bit about what machine learning has become at Google, and especially how that integrates with what you could potentially solve with machine learning, just to give a couple of examples. So as you probably know, Google's mission is to organize the world's information and make it accessible and useful. And turns out that deep learning has become very crucial towards that mission. So if we look at the number of projects that have been using deep learning in the last couple of years, this has grown so much. And this ranges across a lot of areas that you know and products that you really like. And I'm just going to go through a couple of these briefly. I have to mention AlphaGo. You all probably know it. It's really amazing. So people did not expect to have a machine being able to beat Dan 9 player without giving handicap for a while. So handicap means that you are actually favoring the machine a little bit when you're playing. But this was a fair game, and AlphaGo beat one of the best players in the world 4-1. So that's really impressive. And moving more to the product side, I hope you all use Smart Reply and Inbox. I really like it. So Smart Reply is a really nice feature that allows you to save time, especially when you're on the go. So when you're on mobile and you send me an email and I'm just hopping into the train, almost losing it, or the tram, I just want to press on something, and then, okay, that's it, the email was sent. And Smart Reply really leverages machine learning and NLP to kind of predict from the incoming email, okay, what are the possible, should I firstly suggest an automated reply, and secondly, what that reply could be. And this feature has been really popular and taking around 10% of responses sent on mobile. Clearly, recommendation and clustering are really good fits for machine learning, and Google Play Music makes definitely use of that. One of my favorites is Google Photos. So we are having more and more powerful phones these days, right? I used to remember that the time when I was younger and just having to always copy my photos to my computer because I never had space. But now I have thousands and thousands of pictures on my phone, and I just want to search for a picture. For example, when I travel, I took some really nice pictures in Japan, and then I show them to my friends. I don't have to scroll through thousands and thousands of pictures. I can just say, okay, Google, show me pictures of cherry blossoms that I took in Japan, and then it will. And this is really cool, and this is made possible due to machine learning and deep learning in particular. And also related a bit to travel and to vision is this idea of, okay, you're traveling, you're, let's say, in Japan. I have no clue how to read Japanese script, so I can't even type in my search bar what that means. So I can just point my phone to something, and then it will automatically translate. So these are just a couple of examples, and just think when you're trying maybe potentially to solve a problem, is machine learning applicable to what you're trying to solve? And if it is, and if you decide to use machine learning, then you have a couple of sources of complexity that you have to deal with. So firstly, you're going to train your model on maybe a couple of CPUs or maybe GPUs or maybe some specialized hardware. but your users are not going to use the same platforms as you. So you want to potentially deploy on mobile, and there are multiple platforms there. So you have Android and iOS and so on. And these models are also really big. They're getting quite huge these days. So you might want to use, you really might want to take advantage of a cluster to train your model. And you also want to be able to specify really large models. So the image that I have here is the state-of-the-art or almost state-of-the-art image recognition model, and it has a lot of layers, as you can see. You want to be able to specify these kind of models easily. You don't want to have to take months to write such a thing, because then you're really, really slowed down. And the really good thing is that TensorFlow really handles all this for you so that you can focus on what you're trying to solve, right? Like, you don't care about making sure that your model is portable everywhere. You just want to solve your problem and share it with users or play around with it or whatever you want to do. And TensorFlow really deals with all these sources of complexity. So how does it do that? So how does it do all these really nice things for us? So one of the core things to know about TensorFlow and to always think about, so there are two main concepts. One is the concept of tensor. So tensor is just a multi-dimensional array. So if you have a vector, that's a tensor. A matrix is a tensor. If you go to 3 dimensions, that's also a tensor. If you go to n dimensions, that's also a tensor. And these tensors are actually flowing through a computational graph of operations. So that's hence the name TensorFlow. So this is how computation is described in TensorFlow. So it's really important to think when you're programming in TensorFlow or when you're structuring your problem of how your computational graph looks like. So you always, most likely, when you define a machine learning problem, you would want to optimize a loss, and you will define that loss in terms of mathematical optimization that will become part of the graph. And the general procedure when working with TensorFlow is to define your graph, as I said, in usually a high-level language, such as Python. And then this graph is compiled and optimized by the core TensorFlow execution system, and then executed either the entire graph. For example, you have training and testing graphs for different things that you might want to do, or only parts of it. So at testing time, you don't want to execute the part that does the training, and you execute that on the available devices. So how does this work? So the core of TensorFlow is in C++, but if you don't want to deal with that, you don't have to. So you can specify your computation either in C++ or in Python, and these are the officially supported front ends, but I think there are some others available right now. So this is one of the really nice things about being open source. There's a great community out there that really helps with whatever you're trying to do. Probably someone is also thinking about doing that, and there are a lot of TensorFlow users out there that can help each other, and it's building a really, really great community. So now going into one of the sources of complexity that I mentioned before, and this is distribution. So these models, these days that you're training, for example, for image recognition and so on, they are, as I showed, they can be quite big, and you might want to take advantage of the 2 or 3 machines that you might have, or maybe the 20 or the cluster that you have, or multiple GPUs. And you want a flexible platform that is able to deal with that. And you don't want to spend months trying to scale up your training from one machine to multiple machines. And TensorFlow really deals with this quite nicely. So firstly, you can switch from a GPU to a CPU just with a change of flags. So you don't have to change your code. And GPUs are really crucial to deep learning because the kind of computation that we do when we train neural networks is very suited for GPUs. And this is actually one of the reasons why we have all these breakthroughs, is that training a model on a GPU is at least 10 times faster than on a CPU. So if you have a GPU available, you can just change how your network is run, and that's it, you're training on GPU. And you can also use multiple cores or multiple graphics cards. And if you have a cluster or multiple machines, you can also just take advantage of that and just really scale down your experiment time. And now let's just look at some numbers, because I'm selling it here, but I wanna prove you that it actually does this. So this is a graph of training inception. So this is the really big model that I showed that just does image classification. So you have an image and it recognizes if a dog is in that image or another object is in that image. And let's say I want to train this model until I have 0.5 accuracy. So I'm right half of the time, right? And let's see how long that takes with one CPU or 10 or 50 GPUs, sorry. So if I do this with one GPU, it's going to take around 80 hours to train this model. So that takes quite some time. But if I use 50 GPUs, then it's only 2.6 hours. So that makes people be able to experiment a lot faster and advance the field a lot faster and also test your ideas way faster, right? So this is a big scale difference. And the same between 10 and 50 GPUs, you see around a 4 times improvement if you always fix for precision, because that's what you're trying to get as big precision as possible. And as you notice here, so you don't get linearly more performance if you scale the number of machines, because there is an overhead of communication, right? So you will expect this overhead, especially if you have a cluster, there's a bandwidth communication, but even if you use 2 GPUs on the same machine, there is a little bit of overhead there. And this graph is just trying to show you how distributed training scales when you increase the number of workers. So if you have around 100 workers, you would get around 56 speed up over using only one worker. So it's definitely way faster, but expect this distribution overhead, which comes from the fact that you have only one network, so only one set of parameters, and you have to synchronize or asynchronously communicate between these workers. Okay, what is our current set of parameters of the model? Another source of complexity that I mentioned previously was this idea of having heterogeneous systems and complex architectures, right? So I mentioned GPUs just now and distributed systems, but you might also want to put your model on a Raspberry Pi. Why not? Or we also have a certain machine learning specialized hardware which you might want to use, and you don't want to have to tweak that every time and change your code to be able to run your model on all these platforms. And TensorFlow does that for you. So if you have your model that you trained on 10 or 100 machines, you can just take that model and put it on an iPhone or on an Android device. And that's really good. And especially for mobile support, there's a lot of resources out there. And there's even a Google blog about how to just take an already trained model, load that, and create an app that recognizes what's in an image. And this is really nice because actually for this model, you don't even have to train the network because TensorFlow comes with some trained network. So you can just download the network, plug it in your app, and I think in half an hour you have this app that you're able to recognize things. So that's pretty cool. And so why are all these things really important, right? Like in the end, we care about one thing specifically, bringing these great features to users. But if that takes us years, like this researcher has a really great idea, it works in research, but then we have to port it to the production code, and then we have to make sure that it works on 10 million platforms, that takes so much time, then users are always so behind compared to the deep learning research, right? And they're not benefiting of the best possible things that they could benefit of. And that's the really core thing about TensorFlow, because you have all these things available, then you can just go very fast from research to production. And one of the things that was really nice is that it only took 4 months to take something that people weren't sure, does this even work, to actually launching it to users. So that's a pretty good thing to have in mind when you're thinking about these things. So now I'm going to show you a very simple example of how to do linear regression in TensorFlow. If you want to do linear regression, maybe this is not the best way. It's just a pedagogical example. It does work, but there are better ways out there, just as a disclaimer. I'm just trying to show the basic features of TensorFlow, and feel free to interrupt again if you have any questions regarding this. So this is my problem statement. I have a couple of points, and I'm trying to fit a line through these points. So what's the best line that I could fit? So in this case, I know that this is the line because I cheated, and I plotted the line first, and then I generated the data through it. But let's assume that we don't know the line. So we have the point. Whoop. We have the points, and I'm trying to find this line. And then you want to use this, for example, for testing. So if I give you a new point on the x-axis, where should you predict that the point should be? So if I tell you at this coordinate, where should my point be? Well, I learned this line, and I'm going to predict this point here on the line. And in order to learn the line, you have to find the slope and the intercept of the line. So it's defined by two variables. This is the line equation. W and B are the things that we're going to learn. X is the input, so this is the thing on the x-axis, and Y is what you predict. So for training time, you know what Y should be because you have this point. So this is for this X, you know that your Y should be here. For this X, you know that your Y should be here, and so on. But at test time, you will not know what your Y should be, but you will just use this line that you learned to predict that. And now going back to one of the core things that I mentioned before, the computational graph. So every time you think about the TensorFlow program, be it something really trivial like this, or be it a huge neural network with 100 layers and doing something really fancy, always there's a computational graph behind it that you define and that powers the computation in TensorFlow. And at its core, it looks something like this. So this reminds me actually a lot of when I learned operator precedence in school, that plus comes when you evaluate something, there's and first and then plus, and they made us draw these trees. This always reminds me of that. But if you think about what you're trying to do, you're trying to learn W and B, and these things are variables, right? So you don't know them before. You just initialize them with something, and you tell TensorFlow, well, these are things that we will learn. I'm telling you to start with one. I just chose one randomly here. But as we go through learning, we will improve on these things. Now, there's another concept here, which is a placeholder. So this is the value that I had before on the x-axis. So this is the x here. And this is something that I'm telling TensorFlow, well, this will be an input to our program. I don't know it now. I don't know the value now. But when you define the graph, just know that there will be a value in here, right? So it's basically, it's holding place for some value that will come later. And then Y is very simple, what you would expect, WX plus B. And the graph looks like this. So this is the graph that we define. And note that we're not doing any learning right now. I'm just showing a very simple example of how you can compute WX plus B in TensorFlow. So one of the core things to know is there's the graph, but the graph is static. The graph doesn't compute you an output. You are doing this because you want an output. Otherwise, you wouldn't be doing any training, right? But what the graph does is tells TensorFlow this is how computation looks like, but it doesn't do actually any computation. If you want to do computation, you have to create a session and run things through the graph. So this is very simple to create. It's just one line of Python. And this is how the entire program looks like. And this is really important to stress because all TensorFlow programs will look like this, more or less, even if it's a neural network training or something very simple. So you first create the graph. In the case of a neural network, you will replace this with something more complex. And this is the graph that we have created before for WX plus B. You initialize a session. You tell TensorFlow, initialize all the variables. So this is giving W and B the value of 1. And then I'm using the session to run things through the graph. And here, something that's important to mention is, well, I have to tell TensorFlow what the value of x was. I didn't tell it before. I just told it here, well, there's going to be something here, and wait for it until I ask you for something. When I ask you for something, and here I am asking for something, I want the output, I'm actually going to give you something for that. So here, what I'm actually doing, I'm actually computing 3 times 1 plus 1, which is 4, and you will just then be able to get your output. This is a NumPy tensor. So for those of you familiar with Python, it's both the output and what you can feed in the dictionary are NumPy tensors. And that's just the standard way to go about these things. So this was very, very simple. We just computed y if we know w and b. But we don't know w and b because that's why we're doing some learning. And always you're trying to, when you're doing machine learning, you have this error that you're trying to minimize, and that's up to you to define, right? So in the case of classification, I want to tell the network, well, if this image is of a cat and you're saying that it's a dog, then you're wrong, and there are ways to define that. But here, for this simple example, I'm just choosing the Euclidean distance, so these things that I plotted in yellow, and I'm using that for my entire data set. So I'm saying if the line was this one, what would my error be? Well, it would be the sum of this, because this is how off my model is here. My model, when I give my model this x, it will predict this point here, but I actually know that the point is here, so it's off by this much. Same for this point, and for all the other points in my training set, and I'm averaging that, and this is my error. And now I want to minimize that. And how do you do that? Well, very often in machine learning, we use these gradient-based methods. So there are some theorems in mathematics that tell you that if you go into the direction of the gradient, you are going towards the direction of the local minima, at least at a very small scale. So there are a lot of these iterative algorithms. So this is something important to stress, that these algorithms are iterative. So they tell you, go this direction a little bit, then you compute the gradient again, then they say go in this direction a little bit, and you hope that at the end you will end up in the minimum. And with TensorFlow, you don't have to care about the gradient, you don't have to care about even the optimizer. You just tell TensorFlow, well, I want to use this optimizer for my error. So this is exactly what, just putting it all together. This is what we had before. So I'm defining the distance between labels is what I know to be the true value. Y is what I've predicted with the computational graph that we defined before. This is the cost, so the average error that my model is getting. And this is the whole optimization step. So this performs the gradients for you and computes the operation that will do one step. So this, again, does not run anything. This is defining the computational graph. It's just telling TensorFlow, OK, this is what we will be doing, and this is how the graph looks like. And this, under the hood, computes the gradients with respect to the variables that we have defined. So what are we trying to optimize? W and B. And these are the things that you need to compute the gradient with respect of, and TensorFlow does that for you. And now you're defining the session. As always, any TensorFlow program will have that. And as I said, this is an iterative algorithm, so I have to iterate here. I chose 100 times. You can iterate more. There's a whole machine learning theory about how long should you iterate and so on. So don't take this 100 for granted. It's just a illustrative example. And then I'm running this update step. And again, I have to tell TensorFlow what my input was and what my output was. So these are basically my points in the graph that I had before. And every time I run an update step, W and B change such that my cost is smaller. So I'm changing every time I run this. For the first loop, W and B were 1 initially. After I run this step, they're not going to be 1 anymore. They're going to be to the point, they're going to go into the direction of a point that minimizes my cost. And my cost is a bit smaller now. And I do that until my cost doesn't decrease or until I overfit and so on. But this is how a very simple example of linear regression looks like. And now, neural network. So I'm not going to go into as detail of implementing a neural network in TensorFlow because it might take some time. But I do want to show you the options that you have when implementing neural networks in TensorFlow, because there are quite a few, and I think this is also one of the really core strengths of TensorFlow, and this is also why it allows it to be a great platform, both if you want to do research and production. So what's a neural network? A neural network is a very nice model that allows feature learning in a very nice and efficient way. So before, when people did machine learning, there was a lot of feature engineering, right? So if you had an image as input to a model, you had to transform somehow the image from a sequence of pixels, which is what an image is, to something that the model would understand. And what people did is they handcrafted this feature for every problem. So they had human experts saying, okay, for cat versus dog, I think it should be this. And then they they were moving it for any kind of problem. And that's very expensive. Firstly, you need human experts to do that. Secondly, it doesn't scale, right? Like you're just trying to do this again and again. But the really core thing about neural networks is that they learn the features themselves. So you're actually feeding into the model the raw pixels that you have. So you don't have to do any feature engineering. You don't have to be an expert in cat versus dog recognition to be able to do this. And one of the core reasons why it can do that is because of this hierarchical structure. So what it does is that it looks at the input, looks at the pixels, but here it looks at, for example, edges or strokes, and here it looks at even more higher level features and so on. So it turns out that not only that they learn this quite well, they also do it in an intuitive manner. So this is what people would expect, and this is what people were doing before. They were trying to extract edges from images, but instead of doing it automatically, they had handcrafted Gabor filters or something similar, and then they got here. And then from here, they tried to get here. But now you only have this model that learns it all together, and you do something very similar as what we did before with a gradient descent. You define your cost here, which in my case was the distance between the points. Here, we define it a bit differently, and then you backpropagate the gradient. Again, there's the same core thing, the gradient back, and learn the weights between these layers. Now, if you want to do neural networks in TensorFlow, you have multiple options, and there's no right choice. Depends on you where you are on the scale of, I just want to play with this, or I want something that works, or I'm willing to spend 2 months on this versus I'm willing to spend a week on this. And the options are the following. So firstly, you can use already trained models. So for the image example that I've shown, you can actually go to the website, download it, and then use the model. So you just load it, you train it, you don't have to care that there is this complicated beast behind it and that someone spent a lot of time figuring out how to define this. You just use it for your purposes. And I actually have an example of that. Let's see how this works. No, not this one. Yeah. So this, I don't know if you can see this. I have 2 examples here. This is just using a script that comes with TensorFlow, so it even comes with all these nice examples of how to use this, that will live classify this image of a panda. Let me run this. And while this runs, I think it also downloads the model right now, but while this is running, I'm just going to tell you about the script. So the script is 200 lines, and it does quite a few things. So it downloads the model, it does prediction, it's very clean, so it has a lot of comments and things like that, and it also transforms the output of the network into something human readable, because the network is telling you, it's giving you a probability distribution. So the network says 0.1, 0.4, 0.5, and the script also kind of gives us something really nice back. And this is only in 200 lines. So, and there are plenty of other examples out there. So if you really just want something that recognizes images quickly, there is something about that. And here this worked well. So it says giant panda, panda, moon bear. So this looks correct to me. And this is a picture of a different resolution. So it works, just to show that it works at, different scales. And again, it's correct. For those of you who don't know this, and I have to confess, I did not know this until I saw the result, this is correct because this is a tabby cat because of the stripes. So it is a cat, and it is actually a tabby cat because it has these stripes here. So that's what I learned from this. So this is one example, and of course there's not only the trained model for images, there's also a model called McParseface, which actually does semantic parsing for you in English, so you can kind of see the semantic tree, and also this is a noun, this is an adjective, and so on. Now, what if you're not lucky enough that there's already a model out there? So one of the things is that even if it's not in the core TensorFlow library, so this model that I presented is part of core TensorFlow, TensorFlow is open source, so there's huge amount of people actually open sourcing their model. So even if it's not TensorFlow, just have a look on online and see, okay, maybe someone actually has a problem, this problem already solved for me, and I can still just load the model. But even if you don't find that, and you want to solve a problem implementing your own model, there is another option that is very high level and implements the scikit-learn API. So for those of you who have done a bit of machine learning in Python, this is a very popular framework for doing machine learning. It's very nice, clean, and easy to use. And as part of TensorFlow, we have TF-Learn that builds on top of this API. And actually, you don't even have to worry about the graph because it creates the graph for you. So here, if I want to create a neural network with this random set of units, so this means that I have 3 layers. So in the graph that I showed before, I have the input, let's say where the pixels will be, and then I have the layers going up, and I'm outputting 3 classes. So let's say I want to distinguish between cat, dog, or rabbit. Then I can define this classifier, and then I can fit my data through it. So this is also pretty simple. And again, here you wouldn't have to worry necessarily about, okay, this is the computational graph, this is the session, this creates the graph for you. So this is all that you have to specify. And I actually have an example of that too. And I'm going to train one of these models to recognize digits right now using TF-Learn. So this is going to run on my computer live. It's on a CPU, not on a GPU. And it will take a couple of minutes, but maybe we can ask questions during the meantime. But this is basically all it takes. And I made it long because I wanted to showcase some things. So this is how much it takes to learn how to recognize digits using TF-Learn. So the first thing, imports. I'm going to get the data from scikit-learn, and I'm doing a bit of processing because the data comes from 0 to 255, but actually neural networks work better when the input is kind of between 0 and 1 or relatively small. So I'm just doing that too. And now let's visualize a bit the problem. So this is how the digits look like. This is a 6. This is, I would say 7, but I'm not sure. So what we're going to do now is actually train a model to see this picture and say, okay, there's a 2 in this picture. And this is, by the way, the hello world of machine learning. So any algorithm or any benchmark will try this. It's overdone to the maximum. But I had to do it. I had to do it. And it was too tempting. So this is defining the network. And here, again, I made it a bit more interesting just to show you that even if it's very high level, you're actually not losing a lot of the flexibility that you get with TF-Learn. So here, I'm actually saying, define this classifier and use this optimizer. So if you remember, before I showed you about gradient descent and Adam, but there are others that come with TensorFlow. And here I'm saying, no, actually, the default, I think, is AdaGrad, but I'm not going to use that. I want to use momentum. And this is 4 lines of code, and this is just defining the model. So notice there's no graph or session here. This actually doesn't run any computation. This has defined, this has defined the graph. And now I'm actually telling it, well, with this graph, fit the data through the graph. So I'm taking all these images. They are 60,000 in total. And I'm actually training right now for 60,000 steps. And this is, again, training live on my machine right now. And again, it's going to take a bit. Turns out it takes more than 2 minutes to learn how to recognize digits. So if you have any questions now, while this is churning, feel free to ask.
I just wondered, how long did it take you to get into machine learning and all this world?
So I think I'm a bit of an interesting story. So I really like math since I was a kid. Then I studied computer. I decided to go to university to study computer science because I wanted to do something more applicable. So I really loved math, but I didn't like that. I proved something and I just left it there. that was kind of unsatisfactory. So I said, okay, I'm just going to do computer science. And in the second year, I had my course, my first machine learning course, and I was hooked. That was it. And since then, I did my master's in machine learning, then worked here a bit in doing some NLP in Zurich, and now moved to DeepMind. So it was, I guess, love at first sight, if you believe in that.
Is there some other questions? I text near one first.
So thank you for the nice presentation. I would like to ask, like you mentioned, like the DeepMind in London. Could you tell us at least like some small pieces? What are you currently working on there?
I would say just look at our publications. So one of the really nice things about DeepMind is that we publish a lot of the work that we do. So there's also NIPS coming along next week, and there's going to be a lot of our publications out there. So follow that. And there's also the really nice DeepMind blog, where they try to make things very visual. And so, for example, I don't know if you know WaveNet. There was this really new text-to-speech system developed by DeepMind, and it's absolutely mind-blowing. There are samples on the website. You can see how it works, and a lot of other information. So I think the DeepMind blog is also a pretty good place to look at that. And also all our publications are on the DeepMind page as well. So let's just continue with this. I'll also take a bit more questions at the end. So this is done, training. It's saying, okay, I've created the classifier, I fit it. Let's see how well it does. So it's only wrong less than 2% of the time. This is not state-of-the-art. This is far from state-of-the-art. Actually, on this problem, we way exceed human accuracy. So we're way better than humans at recognizing digits on this data set. And I think the error is something ridiculously small, 0.00 something. But it worked. And I think 2% is pretty good for something that just ran on my computer right now, while answering a couple of questions. But let's see what it actually does. So I have here some code that firstly shows us a random example. So what on average we'll probably do right, given that it's not often wrong. So here is a 1. It's saying, okay, this is what the model says. This is the image. So it's say, okay, this is a 1. I think it's right here. Then let's see another one. Okay, this is a 2. But now let's also look at one example where it gets it wrong. So here the model says it's something, but it's actually something else. So here, this is the image. And the model says it's a 1, but it's actually a 2. But, I mean, come on. So, yes, it does things wrong, but also the data is not perfect. So here, I think for some of these things, I would not have known what that is. So this is just another way to use neural networks with TensorFlow. And the last way that I will not show a demo of, and I will just briefly mention, is that if you want to define your model to the matrix multiplication level, so kind of how I did it for the linear regression, you can. And there's really good support for a lot of the things that people use in machine learning, and this is really ideal for researchers. So obviously, it will not be a couple of lines. It will take you way more time to do it, but if you want to do machine learning research and if you want to really play with things, then you can go there. And there are a lot of people who do that. But it's really where, there's no right and wrong. It's really where you are on the spectrum. And just to conclude, so I really think that machine learning is changing the world, and a lot of problems that we thought are not solvable 5 years ago. Just think about AlphaGo, right? And it's just so impressive because it's not only that it beats someone that we thought it would not be, machines will not be able to beat, it did that without handcrafted features. So this is the big difference between Deep Blue, which beat Garry Kasparov at chess, and AlphaGo. Deep Blue knew about chess. They had a lot of human chess experts kind of fine-tuning it and so on, and AlphaGo learned kind of like we learned, just saw a lot of examples, played a lot of Go, and then got really good at that. And I think this is just really mind-blowing to see that we live in a time where these things, all these problems that we thought, this is not going to happen, it's actually happening. And just when you try to solve a problem, just think, could I be solving this with machine learning? And TensorFlow is a really good tool for that, because if you, it's free. There's a great community out there. If you have a problem, you can just report it. People will fix it for you. It's really like a great ecosystem to be part of, and a great community. And you can just do so much with it and with machine learning in general. And that's it for me. Thank you very much.
So thank you. There are some couple of questions.
Hello, thank you for the talk. It was very impressive. I just wanted to ask about errors. We humans, we learn from errors. So I was quite surprised, for example, in this Grammarly tool that you write and they detect your error. And they tell you the type of error and everything's classified. In that sense, how would you try to build this model in ML so that error becomes the base of truth, so to say?
So can you repeat that? I'm not sure I got it.
We have examples from the classification from images, and we have examples from I wanted to say in terms of grammar.
Grammar?
Yes, in terms of grammar, to detect errors, how would you try to model that?
Well, okay, so the question is about grammar, so human language, right? So I think this has changed a lot in the last couple of years. So actually, if you look at language models and what they generate, so there are this, you can train a neural network, a bit of a special neural network that deals with time. You can train it to say, okay, to kind of learn the distribution of words, and you can ask it to predict things. And if you look at what it actually learns and what it predicts, it actually doesn't make that many grammatical mistakes. So there are some really nice blog posts out there where also people try to train such a neural network on the Linux source code, and it actually generates, so it knows how to close the brackets and all this kind of things. It definitely learned the style, right? So also the same with language. Yes, they make some mistakes, but they're getting incredibly good at it. So it's getting a bit far from, again, these things where what people had before, where, okay, this is the noun, this thing in German, you have to put it at the end. These things are, it's just give it some data, and there are a lot of really good NLP models right now, and it will learn for you.
Next question.
Thanks a lot for your presentation. Does TensorFlow support second-order optimization? Like, does it have something like a Hessian-free optimizer?
Yes. I've never used it, but I'm pretty sure yes. So I haven't used it myself, but I would be surprised if not. If it isn't there, GitHub, TensorFlow, file a bug, and probably someone will.
Okay. so I might issue a future request or something like that.
Yeah. So please do, right? Like, this is one of the reasons why it's such a good tool, is because if there's not something there, file a feature request. If other people want it, it's going to be there, right?
Is there another question? Yes.
Hey, so let's assume I'm a complete beginner and I don't know anything about machine learning. What would you recommend? How could I get an intro, or what is the point to start? Because I think that's the hardest part for most of the people who are not yet into.
Yeah, so the question is about how to start with machine learning. Well, I think it also depends a lot on your background. I would recommend different things for people that, let's say, know more math or don't know that much math. So I think it depends. I think there are a lot of courses out there, online courses, that are becoming pretty good. There's also some very introductory blog posts, but just something that I really want to stress, there is nothing like you playing with it. just train one of these models, see it doesn't work, and then realize why not. And for example, if you really want to learn, you can start with something like TF-Learn, like I showed here. But if you just implement it yourself, it will go wrong the first time. And just try to understand why it goes wrong. And there are some subtleties, and sometimes, for example, some of these losses, there's also the numerical stability. So I remember the first time I implemented a neural network, it didn't do anything. And I was, oh God, I chose this career, it's not gonna work out for me. And turns out that there's actually a known issue that now I know and a lot of people know about, but there's this numerical stability issue. But I know that it's very easy for me because I did it the hard way. And I'm a really big fan of, okay, try to look at all these online resources that are out there, and there are some really amazing things, especially some of the online courses. Coursera is a great example, and Jeffrey Hinton, who is one of the parents of deep learning, he has a Coursera online course, which goes also quite deep, so it depends, again, where you are on the spectrum, but there's really nothing like getting dirty and seeing, okay, I'm trying to do this, it doesn't. And there are some data sets out there, so NIST is available, you can play with that. There are also some language data sets, so one of the nice things that you can do, there's some of movie sentiment analysis data sets, so you get some movie reviews, and you try to predict if they're positive or negative, if the person liked the movie or not. So you can just play with that after you learn a little bit, but there's nothing, I personally really believe this, there's nothing like getting it wrong and learning from that.
Cool. Yeah, okay.
And where do you see the limit with artificial intelligence?
Is there a limit? I don't know. I think it's very hard to say because we're moving very, very fast, and some of the things that I would not have thought possible a couple of years ago are possible now. So recently, there was these papers that showed how to do what we call like one-shot learning. So basically, you learn how to translate between Korean and Japanese, even though you've never done that. You've only know how to translate Korean to English and English to Japanese, or some strange thing, and it's actually working remarkably well. And 2 years ago, I don't think I would have thought that's possible. So I think it's very, very hard to say. I think we're still far from what we can do, very far. And especially things in, I think using things like reinforcement learning, I think reinforcement learning will grow a lot, because a lot of these things that I've shown now are just, okay, I give you this set of examples and learn from that, but that's not what we do, right? Like I go through life, I get rewards when I do something well, and I get punished when I don't do something well. And I think this is something where we will see, my personal belief is that we will see a lot of changes from that.
So we have here another question.
Hi. Thank you for the presentation. Is there a way to harness the power of Google clusters to train the models? Because we do it now locally, but complicated model.
Yes, so there is Cloud ML. There is a machine learning API out there. It is powered by TensorFlow, so you do use TensorFlow under the hood. Yeah, so the answer is yes.
Last one, the last question. Oh, there we go.
What about doing different things with the same AI, like image recognition and text-to-speech or something?
So the question is, how about doing different things with the same AI? So definitely that needs to happen, and it is happening slowly, but I definitely agree that we are not, so there are some things, like for example, people play the different games with the same model, so the completely different games, but it's still far from having, once we have a model that can do multiple things, because I'm talking to you at the same time, but my brain is pumping things, and it's just insane what our bodies are doing, but our models are still, okay, this is a cat, oh no, this is a dog, so we're getting there, but definitely this is, I think these are the two things to stress about, reinforcement learning and having models that do multiple things. Yeah, it's definitely possible. It just, I mean, it also depends what do you mean by model, because you can have a very simple model that says if the problem is X, delegate a model that knows how to do X very well. If the problem, and then you have a model that does all this. No, I agree with you that you should have one model that kind of figures these things out, but we're definitely getting there. And also one of the other things is that, for example, translation, right? I think soon we're going to have one model that knows how to, just like I showed, that knows how to translate multiple languages. So it's not two different tasks, but it's still getting there to the point, okay, we have this thing that knows how to do more things than we initially envisioned.
Okay, last one.
To follow up his question, combining different models into one, do you think we can get to the point where we can replicate human behavior in like computers, like really general behavior of humans?
That's a hard question. Can we replicate? And also, human behavior is a bit undefined. So it's very hard to say, what do you mean by human behavior, right? I think we can get very far, but I don't know exactly what you mean by human behavior. And I think we should strive for that. We should strive for generic learning, and I think that could help us with a lot of things. But and I personally am confident that it will happen. But I don't. It's very hard to say, right? Like it's a really fast-moving field, and that's what gives me confidence that I think it will happen. But I can't tell. No one can tell you for sure. It's going fast, but we're still in the early days. So fingers crossed.
Thank you, Mihaela, for the amazing talk. Let's make warm applause for her.